Now there is this another diagram. Hmm, probably this will clear most of things if you still have doubts. It's called queuing diagram. So ready queue, Q U E U Q. It goes to CPU. Okay, CPU can either terminate or input output request. Input output Q U E U ready queue. Okay, and let's say time slice. Yes, time slice as expired. Now, what does this mean? So, let's say this is CPU and this is CPU and this is process 1, process 2, process 3, and process 4. Okay, it goes in this order. Every 2 seconds, every 2 seconds, processes change. Now, CPU will have process 1, will have process 1. No, after few 2 seconds, this will be suspended and process 2 will execute. Yes. So CPU process then process 3 will execute. Then process 4 will execute. Again process 1 will execute for every 2 seconds. This sort of round robin thing is called what is happening is time slice expiry. Okay, and we might fork a child. Okay, and child executes. Once this is done, again the parent can go back to ready queue. Or the child will execute and this child can go to ready queue. Yeah, that is better. So this is shell, this is fork, okay, and creates a child, okay. It's called Spotify, okay, and this will go to ready queue. Once this will suspend, this will get suspended. Once this is done, again this will go to ready queue. So that's the idea. And wait for an interrupt. Interrupt occurs. Some signal is happening. Okay, imagine some signal is happening. It is gone back. This is a queuing diagram. So now the thing is, now we know what's a process, and we have studied different components. Building upon these components, we studied about PCB. So this gives the character of the process, character of process. So since we have a character of process, we have a way to quantify it. Okay, we have a way to quantify the process. First, the character, quantify the process, and then we've studied the states of process, or we can also say this is the lifetime. What the process has been doing for a long time. Okay, this is called a lifetime, and we know that for a program to become a process, it has to be loaded into memory. First of all, this has to be loaded into memory, and for the process to compute something, it needs the CPU. Okay, to work. Okay, it needs the CPU. Now we are going to look at the algorithm or the protocol. The OS follows to assign the CPU to the process. And from here, we are going to launch into another topic called scheduling algorithms. So we'll look at this in next lecture. So, alright. So, in this video, we're going to look about scheduling algorithms, which is also a continuation of short-term scheduling. Right? And there are a few topics or components which we have to be clear. So, first one is preemptive scheduling. The other thing is dispatcher. Alright. So let's say, so this is some job is going on, and this is the lifeline of the job. And this job gets over by 20 milliseconds. So this is the time taken by the job to complete. In between, let's say a 10 millisecond, we are going to interrupt this job. I mean, we as in the CPU is going to interrupt. CPU is going to be interrupting a running process. Okay, so this is going to happen, and we are going to assign the CPU to another process. Okay, let's say process 5, some another process. So why are we doing this? There are some considerations. Let's say the priorities change. So this process P5 is in higher priority. So maybe we are going to change for that, or time considerations, constraints. Let's say the time is constrained. Every job, no matter however big it is, even if it's going to be 20 milliseconds, the time limit is 10 milliseconds only. So after 10 milliseconds, it is going to get interrupted and it is going to be taken out. Okay, so this is called preemptive scheduling. Preemptive scheduling. Okay, now we know that there's a component called preemptive scheduling, and it interrupts the running process. So that we know. But what actually is interrupting? So evidently that is the dispatcher. So yeah, we have this ready queue. Okay, we have this ready queue, and we know that short-term scheduler will take a process, and it will assign the CPU for the process. Let's say this P1, and this P1 is getting blocked, and we know this is done by medium-term scheduler, and submitting all the jobs in the ready queue is done by long-term scheduling. Okay, blocked, and maybe this is waiting for some input and output resource, so this is getting blocked. Now in the meanwhile, we know that there are some other processes in the ready queue. We are going to pick one and we are going to assign it to the CPU. So P3 is running and P1 goes back. So this process switching that is actually being done, it is done by the dispatcher. Dispatcher does the process switching. It's also called as context switching. Okay. So to summarize this, preemptive scheduling allows the CPU to be taken from a running process while the dispatcher is the component that performs the context switch to transfer control to the selected process. So preemptive scheduling will interrupt the CPU while some process is executing, and dispatcher is this thing that gives the control of the CPU to the process, which was selected by short-term scheduler. So short-term scheduler selects dispatcher will give the control, right? And scheduling which is happening, like we know the short-term scheduler selects and it schedules, let's say process 1 is running, okay, you're done, now you should go process, that thing is happening, right? So that is actually we follow few algorithms, and there is a criteria on how to select and what to select. That criteria, it contains of certain important topics that which we are going to look at. Scheduling criteria. So there are few topics. CPU utilization, first of all. So CPU utilization is, it's to put it in a simple definition, we are just going to keeping the CPU as busy as possible. So if there is at least one process that is going to run, then the CPU is utilized. So there must be at least one process. So that is CPU utilization. And the next thing is burst time. So burst time is the total time a process requires the CPU for execution without waiting or interruption. So let's say this is process 1 and it will have some metadata, okay? Let's say this process 1 is going to arrive at 3 milliseconds. Okay. It arrives at 3 milliseconds and its burst time, let's say 20 milliseconds. So from 3 till 20 milliseconds it runs. So that's the idea of burst time. And we have throughput. So all these what I'm doing right now is basic definitions. So I'm not going to spend much time on explaining it in detail, because we look at scheduling algorithms, which is important. So throughput is number of processes. Okay, this hash symbol is number of processes. Process is also called as unit of work. Yeah, we already looked at this. So we are going to use process to quantify the amount of work being done. Okay, and that are completed. Number of processes that are completed per time unit. Let's say for 2 seconds or 5 seconds. In 5 seconds, how many processes has completed its work? So that is throughput. So turnaround time. So a process is being submitted to the system, and this is the completion. So this is submission, this is completion. So we have the total time. So this total time from submission to completion is called turnaround time. Okay. So in between, the process can get blocked or suspended, or it goes to wait for some resources. So everything, the total sum, is the turnaround process. Next, we have waiting time. So waiting time, as the name suggests, it's the sum of the periods spent waiting in the ready queue. So from the disk, we are going to give schedule it to a job. So job scheduling will happen, and this will be in the ready queue. This is the ready queue, and from ready queue we'll dispatch with the help of short-term scheduler and dispatcher to the CPU. So let's say there's a certain job that is waiting to get dispatched. Now, how much time it spends here? So that is the waiting time. And we have finally we have response time. Response time is very important time sharing system. So I'll tell you why. And again, we're going to submission till completion. Okay, we're going to submit it to the system, and this is in the middle. We are going to get the first output. Some calculations were done, and the CPU the OS thinks, okay, the amount of work done is enough so far, and we can give a proper response. So the from the time of submission to the time of first output, so that is response time. Right. So I think these things are clear. Now we'll go into schedule.